Okay, so before we get started, just a quick reminder. So like pretty much after, I mean, not pretty much, for sure, after every lecture, I'm going to post the lecture notes and also the video. But I think I mentioned it on Tuesday that sometimes depends on like how fast the staff post the video. Like it might takes like a nine, especially when it comes to the middle of the semester when everyone gets really busy, then the speed will become slower and slower. If you have taught and upload the video, then you know what I'm talking about. So the best strategy is definitely for you to come to the class so you already know what I'm talking about. And then later on when the video is posted, then you can actually do a second or third review. So another thing I want to remind everyone is that as you can see, for those of you who already start reading the textbook, that there are a lot of prerequisite about topology that you need to know actually. So I would say that please start reviewing some of the material that at least that textbook mentioned, or at least when I talk about it in the class that I mentioned in the lecture notes or actually in the textbook. And if you just want to have a list of the topology terminology that they use, you can actually see that I think the author did a pretty good job, like included in the appendix. And other possible references I already posted on the Blackboard. If you go to the course material, below where I posted the electronic textbook for this course, you can also see a couple of like reference. I mean, each of them has their own good and pro and con. So I think the most thorough one, in my opinion, is John Lee's introduction to topological manifold. It probably contains too many things, so you might like find it a little bit too much. But the other references I posted there, that is either kind of like a lecture notes or some small book, so or maybe more like intense. So it depends on like people's taste. So if you could find any of the reference, I think that will be good. And as I mentioned, I already sent an email to the librarian and to request electronic version or access of the book that Introduction to Topological Manifold. I don't know when they will actually get back to me. I hope they can approve that. I think the librarian actually promised me that this is okay, but it takes some time for them to approve it. So as I said, once I know that it's there in library, I'm going to email you. And another thing is that after today's class, like hopefully by the end of tomorrow, I'm going to post the part one of homework one. So you're going to see that some of the question, I will design some of the question, or actually, if I'm going to assign the exercise from the book, it will be from our textbook. So I will make it clear. Okay, so today I'm going to continue some of the examples for so you have a copy of Moncrief and Burn's topology. Yeah, so I mean, the things that right now everyone is like. So if anyone, so Matt Tarker just said that if anyone, he actually has a copy of some of reference book. So if anyone needed, you can ask Matt for the reference. But I'm trying to look for like online, possibly online reference, so people don't need to actually come into the campus and still can get some reference. Okay, so for topological manifold, I want to do a couple more examples. Some of the examples are more involved, like the one that we're going to talk about, like projective space. That's quite involved, okay? But others that it's kind of for free in the sense that like, so on Tuesday, we already know that if you have a topological space, for example, and if you have a subspace, you can equip it with subspace topology, right? So then you will have essentially some nice property inherited from the ambient space, right? So as a subspace with subspace topology, it's automatically Hausdorff and second countable, right? So in some sense, all you need to prove is locally Euclidean. That's the three property you need to check for a topological space to be a topological manifold. Okay, so usually like the first two, the second countability and Hausdorff are kind of easy in some sense. And so last time, the very last thing we did in Tuesday's class was that we create what we actually was given a continuous function like what I wrote here. And we know that for a continuous function like this, if you consider the graph of this type of continuous function, either from some, and it's very important that it's actually from an open set U in Rn, right, to some dimension R to the K, right, then it's actually, we just proved on Tuesday that it's a topological manifold. And I want to specify that that this is, so I want to just remind you that this can be proved that it's actually, the reason that it's a topological manifold is that once you have a graph lies in ambient space Rn times Rk, then you can actually use a subspace topology, right? And then you prove, last time I think we proved that it's locally Euclidean, okay? So it's actually a topological manifold. So if you can turn anything, or if you knew that this topological space locally, if it looks like a graph of some function, then in some sense, we can come back to use what we already know, right? So it turns out that the second example I want to show you is something really new. Like especially if you're trying to recall when, long time ago when we were in 720 curve and surface class, what we actually did is to represent, one of the way to show that a sphere is a regular surface is that we're trying to cover the sphere into several patch, right? And then each patch locally looks like a graph of some nice function. This is what we did before. And I'm going to just quickly recall the process. But the only slight difference is that this time we are going to do an n-dimensional sphere, right? You can imagine that although I cannot draw an n-dimensional picture, but the idea or the process, the argument should be more or less the same. So we consider what we call the unit n sphere, right? And we use this notation s to the n. And basically it means that any point, I should be a little bit more precise, any point in to the n plus 1, which satisfy the magnitude or the radius equals 1, right? You collect all the possible points. And I want to show that it's a topological manifold. Okay, first of all, I need to convince you that we can equip a topology there, right? So then it first is a topological space. But I'm going to be a little bit sloppy here because essentially you can imagine that Sn, this n sphere, you can equip it with topological, subspace topology, right? So basically you equip with subspace topology, right? So then in that case, it will become a topological subspace of R to the n plus 1, right? So basically let me remind you what's a subspace topology. It's actually, you can say that an open set, a set in on the sphere is open if it can be written as the intersection of an open set with Sn, right? So this is basically the subspace topology, right? So it's quite intuitive actually. So if it's a subspace like this, topological subspace, then as I just mentioned, it should be, we can prove that this is the exercise I assigned, like practice, that that you can prove that it's automatically Hausdorff and second countable. So that's why a topological subspace is kind of nice, or essentially you can say the subspace topology is a well-defined or has a good behavior. So now the only question is we want to prove it's actually locally Euclidean, right? So the second part I want to prove locally Euclidean. And the strategy I can tell you now is that I want to essentially decompose the n sphere here into several graphs of some continuous function, right? You can imagine that Sn itself, the whole thing globally, is not a graph of some continuous function, right? Because it can actually not represent the whole sphere. But if you cut it half, for example, right, then you can represent the upper hemisphere into a graph of a continuous function. And you already kind of know what the graph is. It's usually how we solve the sphere equation, right? And you have lower half. But then since we want the open set, right, the domain to be open set, you will miss the equator, right? So then you want to cover another two, I would say east hemisphere and west, right? Then when you put it all together, it depends on the dimension, right? So in total, if it's an n-dimensional sphere, you need 2n plus 2, a patch essentially. So the idea is like this. So if you already read the textbook, you will see that they're trying to write it very rigorously in the sense that they really explicitly tell you where's the domain and what's the function, the continuous function looks like. So I'm going to write the detail down so you can actually refer to. So first, I'm going to define an open set. So I'm trying to be as consistent with the textbook as possible. So now let's define the open set. So there's several patch. So I'm going to call it UI plus. And UI plus is essentially, you can think of that it's a upper half space. So this is collecting all the coordinate, all the points in Rn plus 1, such that the i's coordinate is positive, right? So I can be any number, right? So it can be 1 to n plus 1, right? So you can think of if it's the last coordinate is the usual upper half space that we know of. And this is definitely an open set, you can imagine. Okay, and then we can also define the same thing, right? We can define UI minus, right? And you can imagine this would be the one with i's coordinate negative. Okay, and again, you can think of this is lower half space. This is also open set. Okay, now I want to define another map. Later on, this is actually my graph, the continuous function for my graph. So now I call this F, and it's going to, the domain has to be an open set. So that means, let me take the domain to be open bowl, okay? So that's, this is opened unit bowl in Rn minus 1. So it's n-dimensional bowl, okay? And it maps to R. And the definition is whenever you plug in a point in the open bowl, then this is the definition. So this is the norm square of U, right? So you can imagine this is actually how we define, or essentially how we solve the upper sphere equation, right? Okay, so now this is essentially, I already kind of tell you, this is exactly the graph that we need. So, so this is for each. So now let me make it precise. So now the thing is that we want to make it precise. What would be the coordinate domain, right? So for each point, so what's locally Euclidean means, it means for each point on the sphere, I need to be able to find an open neighborhood such that it's homeomorphic to some open set in Rn, right? So now I need to make it precise what this open neighborhood looks like. And as you can imagine that I'm going to separate the sphere into different type of like half sphere.
Professor, why we are defining this on Rn plus 1, not, I mean, why is it not Rn?
Oh, I haven't done yet because the thing is that, you mean like which one, the open set UI?
Yeah.
Yeah, actually, I need to intersect it with the sphere. I haven't done it. That's the next step. Yeah, you're right.
Okay.
My open set, the open neighborhood need to be R on Sn. Yeah, but I think the textbook is a little bit redundant that he want to be very precise. That so what I'm going to do is taking UI plus intersect with the sphere. So you will have essentially upper hemisphere and lower. Yeah.
Okay.
So, yeah. So let me okay, give me a second. Yeah. Otherwise, that it would not be correct. So let me write down everything. So I can explain it in a minute. Okay, so first let's just take a look at the plus situation. So later on we also have negative, right? So now what's my open neighborhood on the sphere, right? So essentially I'm taking the intersection of Sn with the upper half plane, right? So this basically means that you only want the upper half in some sense. If you, not necessarily upper half, right? Depends on what I is. If you choose I to be n+1, right, the last coordinate, then this is essentially half of the sphere, right? When xi is positive. So that's why I called it upper half, right? So you can think of the upper half sphere is the graph of the following function. So here I want to introduce a notation here, right? So you're essentially, what you do is that, okay, you take the usual equation for the sphere, right? You have x1 squared plus x2 squared all the way till x to the n+1 squared equals 1, right? How do you solve this function, right? How do you solve the sphere, half of the sphere as a graph of some function? Then you essentially, for each I, you pick out the I, you're trying to solve what xi is, right? So then you can see that the remaining coordinate, there's only n coordinate. That's why technically we know Sn is an n-dimensional manifold, because we only need to use n coordinate to represent it. The n+1's coordinate can be solved or represent in terms of the other n coordinate. And here, if you already read the textbook, you will notice that they have this notation like a xi to the head. That means missing or don't have i's coordinate, right? So that means that entry is not there. Okay, so if I is say n+1, right? So let me give you an example. If I equals n+1, that means I represent n+1's coordinate into the first n coordinate, right? And this is essentially my function here. Probably this is more clear. What does it really means here? So this is my function, right? So you can imagine, like, if you want to use two sphere, right? So essentially you solve z coordinate as square root of 1 minus x squared minus y squared. Or the other round, if you choose the first coordinate, then you solve x equals square root 1 minus y squared minus z squared, right? So you can do that for each different coordinate. And so basically, in the picture wise, let me draw the picture. Then you have, like, imagine that's upper hemisphere, right? So upper hemisphere is the graph for the front, and then you have this domain here, right? This is your domain, and then this is the graph. You can go up, and then this is the upper hemisphere, right? If you think of this is actually x to the n+1, and the bottom one is r to the n, right? So this is essentially, you could represent the upper hemisphere as a graph of some continuous function, and it's given by this f here. Okay, so I think I need more space here. So this is just like a more precise way, like if you really want to write down explicitly what the function looks like, this is how you can do it, right? So basically, this is when xi is positive, right? Then what about, then there's the other half, right? So you should also do the same thing, but it's pretty much the same thing, that then we can also have, this is what I call like a little bit misleading, but this part of the open set on Sn, this is the lower hemisphere, is also the graph of the function, continuous function actually. Then now you want to represent the lower half, right? So your function should be negative here. And again, you are taking out the i's coordinate here. So i's coordinate is not here. Okay, so you can imagine this would be solving negative square root of something, 1 minus something, right? So then I'm not going to do all the detail, because this is very similar to what you saw in the graph example. And you can actually prove that you can actually map this open set to Rn, right? So basically, you can show that I have actually a homeomorphism here. So my homeomorphism is essentially, you can define like this. Okay, so let me first write down everything. So actually, I haven't really explicitly tell you what the homeomorphism is, right? Because you can see that all I tell you is how to represent an open neighborhood or some part of the sphere into a graph of something, right? But you also can actually write down explicitly what the homeomorphism is. That will give you the property of locally Euclidean, right? So for plus or minus, just like the function here really depends on like which graph you're talking about. Then, so this is be your open neighborhood that Ibrahim was asking. So the open neighborhood on Sn, right? So for each I, you're going to map something into Rn, right? And then the homomorphism is defined by the following. Actually, we take the homomorphism to be the projection, right? Actually, if you go back to check what they were doing in the graph case, or maybe if you want, you can go back to the curve and surface case. Actually, they all do the same thing. They first start with the projection map for this type of thing, right? So first, we essentially, what we do is that we take this upper hemisphere, right? You do the projection down to Rn, and you project onto, either you project upper half to Rn, or you kind of project, depends on how you say it, you project the lower half to Rn, right? And which one do you project? You project exactly to i's coordinate, right? Sorry, I should say to the plane that without i's coordinate, right? And then how do you find the inverse map going back, right? So inverse map would be whatever the first n coordinate, and you pair with the last one would be your graph, right? So basically, this is essentially this phi here would be the homeomorphism. Okay, so I'm a little bit trying to like speed up here because I think I'm doing something repeated as the first example we did on Tuesday. So I'm trying to be speed up here because we still have a lot of example. So I'm going to rely on you reading the example 1.4 in the book. And I should say you should combine with the graph example, which is, I think, is 1.3 in the book as well. Okay, and if you want, I would encourage you to go back to, if you are not comfortable with n-dimensional situation, then you can actually first think about how do you deal with it if this only, if it's a sphere, like a surface, right? And you can actually check the curve and surface book that we used before. Okay, any questions so far?
Could we not also prove this using product spaces?
As to the n, how do you do product space?
Um,
How do you want to represent it as n into product of what space?
my my initial thought when you asked the question was to form neighborhoods in R
Mm-hmm.
and take the product of them accordingly, and then form an intersection between them and Sn, and
But
show
this
that
is not product space, right? Product space means you want to show s to the n equals, say, m1 times
I see what
m2.
you're saying.
Yeah, so
I see
I
what you're
don't
saying.
think Sn can be represented as a product space. Yeah,
Okay, I see
yeah,
what you're saying now.
yeah.
Yep.
Okay, so now what I want to do next is that, so basically why we care about topological manifold is that, so first of all, it has some nice structure. It locally looks like a Euclidean space, okay? And once you know one or two or some topological manifold, you can actually create more by doing some, in some sense, like construction or surgery, right? I don't want to call it surgery, so it'll be misleading. But first, we already know if we have a topological space, then the subspace equipped with subspace topology is a nice space. So a lot of time you can actually prove it that it's a topological manifold. Okay, but we can also create something larger, right? So another example, which I kind of directly jumped through, this is I think the last example when you read the textbook, they have this product manifold. So product manifold is another way to create a new manifold from an old one. Okay, so so the setting is the following. If you already have K topological manifold, and each of them does not necessarily need to be the same dimension, okay? Then the product space essentially is what you think of that M1 times M2 times MK. And what's the element in it? It looks like, let's say, let me use different points. So it's just essentially a collection of K tuple, right? Where each point Pi lies in the each manifold, right? So this is essentially the collection of all such points is what we call the product space. And on top of that, we want to equip this product space with product topology. So the one typical example, if you cannot imagine what this is that actually if you think of R to the K, right, the Euclidean space to the K dimension, you can actually in some sense think of that this is essentially a product manifold, R1 cross R1, and then you do K times, right? Because R to the K, how do you represent it, right? You essentially collect all the points. I mean, you have K coordinate, right? So each one is from R1, essentially R, right? So this would be a topological manifold of dimension n, which is equal to the sum of each dimension, right? So you can see that if you have R2 times R1, that will be essentially, you can make it homomorphic to R3, right? So now the topology we want to put on it is what we call the product topology. And there are several ways we can define a topology in the sense that either I can show you or tell you what a topology is, and then you can find me a basis. But another way around also works. Sometimes you can tell me what will be the basis is, and you use this basis to create a topology. This is usually what we call the basis generated by, the topology generated by the basis. Okay, so basically, I may not have enough time to really re-expand everything. This is actually the product topology is actually something I would think of as a review. So you can actually check either the appendix or one of the reference there, right? Or you can actually Google it. This is a very standard topology topic. So you can see that when people talk about product topology, how do they set it up? But I can at least tell you under product topology, what would be the basis here, right? So it's very intuitive, right? You would think of how would you define an open set on such product space, right? While each of them is already a topological space, okay? Then the basis intuitively should be a collection of all the set looks like this, right? You take each UI would be an open set from each manifold MI, right? So you take all the open set and times together, right? You do a product of it, right? So you have U1, which is an open set coming from M1, and you times U2 and all that, right? So this type of collection of open sets should be the basis for your topology. Then you will ask, what would be the topology? What would be a typical open set looks like on this product space? Then it turns out that a union of any type of this open set in B, it's going to be our open set. So an open set in product topology is a union of sets in B, right? So which means that if you want to generate a topology, the product topology from this basis, then you essentially collect all the possible union of all this type of open set, U1 times U2 times all the way to UK. Okay, so that's the topology we're going to put on the product space. So now you can imagine if you have like K topological manifold, then the product of it should also be a topological manifold, right? Like it's kind of, I mean, at least we're talking about finite of them, okay? Infinite many of them, it's a little bit tricky, but finite of them can be easily done, okay? So that's why I don't want to put too much detail in it because we still have other more important example to go. But I'm just going to tell you what would be the property here. So this is the exercise that also not hard to do. So I would like encourage you to do it by yourself. If you have any question, please let me know, right? Or possibly I bet you can find the answer on the internet. There's so many material out there. So if you have k of you have k of them topological space. If each of them is Hausdorff, then you can actually show that the product space is Hausdorff as well. Okay. So first of all, we already know the product space is a topological space equipped with product topology. Now I want to show that you can actually check the three criterion to show that it's a topological manifold. Okay. So first we will encounter the Hausdorff and second countability. And from this exercise, it shows that we can prove if each of them is Hausdorff or second countable, then you can show that the product space is going to be Hausdorff and second countable. Okay, so this can be done similarly to the case that when we're trying to show the subspace topology is also the case. But now, what about the third criterion, the Euclidean, locally Euclidean, right? Which means that you need to find me a coordinate chart for each point. But this is also very intuitive, right? You already have coordinate chart for each manifold. Why not just put it all together, right? So it turns out that because each of them is already a topological manifold, so for each point, I can find a coordinate chart, meaning this phi I is my homeomorphism, right? And this is the open set, right? So for each point, there's exists such coordinate chart for each manifold, right? But what about if you times it together, put it as a product, right? Then you can imagine you're going to put the open set all together, right? So this U1 times U2 all the way to UK, this will be open in the product space. But now you need to kind of a little bit justify what this map means, like phi1 times phi2 all the way to phi k, right? So we use this definition. We say this is just an abbreviation of that the first kind of component you put phi1 of x1. So if you have a point x, which essentially come from the product manifold, right? Or actually, to be precise, come from the each U1 to times UK, right? Then you're just plugging into phi1, you're plugging x1 into phi1, right? And second component will be you're plugging x2 into phi2 and all the way to phi k of xk. So you kind of like just plugging the corresponding points into the corresponding map, right? And this definition of map, you can check that using the product topology, you can show that this is going to be the homeomorphism, that this phi1 times phi2 all the way to phi k is my homeomorphism for the product manifold, for the product space. And using this, of course, you can further check that not only it's continuous, this map will also be, this product map will also be a homeomorphism. Then this will be indeed give you the homeomorphism you want to prove the locally Euclidean property. Okay, so essentially, I just want to introduce that once you have a couple of topological manifold, by doing a product like this, you can create a new topological manifold. And this is actually quite neat because there are several, or actually many of the manifold can be represented as a product, right? So for example, as I said, you can view Rn as a product manifold, right, as well. And the typical one that usually people represent is the torus. So this is usually this is the torus that everyone think of, that the two-dimensional torus, right? And how do you view it as a S1 cross S1? In some sense, you can think of that you can see a circle here and another circle here, right? So it's like a surface of erosion, right? So then you essentially like swipe through a circle by one circle, right? So that's why you can actually prove that S1 times S1 is homeomorphic to the torus T2. And in this sense, we can actually define an n-dimensional torus. And usually people use this definition that Tn is essentially S1 times S1 for n times, and we called it n torus. So you can see that by knowing, or essentially if we are able to prove product space is a topological manifold, then right away you're telling me torus or n torus is actually a topological manifold. And there's so many different combinations you can do, right? As long as you're times like some topological manifold together. So I would suggest that you also take some time trying to take a look at how people define the product topology here. So at least you know how to equip them with the topology, and then convince yourself that to create a coordinate chart on such product space is actually not that hard once you already know the coordinate chart for each like component, for example. Okay, so this is essentially, if you know some topological manifold, you can do a product space to create a new one. But another example I want to say here is actually I need more preparation. And some of them is not in the textbook in the sense that like it's not in the usual content. Some of them I put it out from the appendix. Some of them I just introduce myself, right? I may not say it in the correct order. So you can definitely check the reference for some of the things that I mentioned here as a review. Okay, so if you never took a basic topology course before, this might be a little bit intense for you. Okay, so you definitely need to go review some of the terminology here, and definitely let me know and come to the office hour if you have any questions. Okay, so as I said, if you know some topological manifold, you can do a product space to create a new one. This is another strategy of creating a new one, but it's a little bit different. We're going to create a new space or new manifold through quotient, in some sense through equivalence relation, okay? So first, before we talk about equivalence relation, I need to remind you what a quotient means, or quotient topology, okay? So let's say we start from a topological space. That's essentially usually the model we start from. And Y is just a set without a topology. Now we need to define a topology on this set Y, okay? So first we need to do it through a surjective map, okay, from X to Y. The model you can think of, the test example you can think of here is the projection map, right? Projection map is usually surjective. It's usually the model case we think of. And how do we define a topology on Y? We say a set U in Y is open if the preimage of U through pi is open in X, right? So it's kind of like you pulled it back to X, right? You don't know how to define a topology on Y, but you essentially put it back to the X, right? Then if pi inverse, I shouldn't call it inverse, the preimage of U actually is open, then we say U is open. That's essentially how we define a quotient topology through this map pi. And because of this quotient topology, we call pi to be a quotient map, okay? So this is the terminology we're going to use from now on. So you can imagine to define a quotient topology, I also need this quotient map pi. I need to tell you what's the map pi here, okay? So now let's see. So we want to consider a more general situation, because it might be the case where we can equip Y with some other topology. So if the topology on Y is explicitly, in particular, the quotient one, then we also call it quotient map. So let's see. So now in this definition, let's say X and Y already are topological space. And we have some map from X to Y. It's already surjective and continuous. Then in this case, we would be able to call pi as a quotient map if the topology on Y, if the topology we put on Y is exactly the quotient topology. So you need to be careful here, right? You can always define different topology on Y and make some map to be continuous, right, and surjective. But this topology on Y may not necessarily be the quotient topology, right? But if in particular the topology on Y is the quotient topology, then we call this map pi to be quotient map, okay? But the things that you need to see that when it's really the case, right? So there's some criterion you can check. Okay, so then with this definition, now one one of the reasons we like to deal with quotient map is that it actually also in some sense carries some nice property. So this is actually usually, if you read the literature, most of the time people call it characteristic property of quotient map. Okay, so actually this is included in the appendix, but I think it's in one of the theorem. I don't remember the number, but I just put it here, put the name here because this is the common name people code it. So it says if you have a quotient map from X to Y, so meaning this map should already be continuous and Y should equip quotient topology, okay? And of course, the map should be surjective, okay? And it says if Z is another topological space, then we have a good property. Then a map from Y to Z is continuous if and only if F compose pi is continuous. Okay, so I'm going to like draw a picture here, like a kind of like a diagram, so you can see it more clear. So we have a X to Y, that's a pi, right? This is quotient map. You need to have a quotient map to start with. And we have Y to Z, this is F, right? And now you can imagine that we can close up the diagram like this, right? So this will be F composed pi, right? So this tells me that, of course, I already know pi is quotient map. So by the definition, it's continuous. But this with this diagram, you know that if one of them, either if F is continuous, then F composed pi is. The other around, which is the one we are going to use it later on. If you want to show if you want to show F is continuous, you can show that by showing F composed pi is continuous, right? So either way, so you can actually, the best way to remember this theorem is actually to do a diagram like this, right? But of course, you need to have a quotient map to start with. That's why we call it characteristic property of quotient map. Okay, so essentially you obtain some kind of continuity through the quotient map. That's the sense. Okay, so now once we know roughly what's the definition of quotient map and quotient topology, then a typical example of using or a typical example of some space with quotient topology is what we call the quotient space. And it's going to be defined through equivalence relation. Okay, so first we need an equivalence relation, right? So let's say this, we usually use this delta to be an equivalence relation in a topological space. And we define this bracket of X, what we call the equivalent class, right? If you take some algebra class, you probably already knew this. This appear a lot in some of the algebra class. So what this equivalent class means, it means you just collect all the possible elements such that is equivalent to X. Okay, so it's like a collection. Okay, so now I want to stop here. I want to make sure everyone is on the same page in the sense that, does everyone remember what an equivalence relation means? What's the definition of equivalence relation? Does anyone want to say? Okay, I saw someone give me yes. Do you want to, does anyone want to explicitly tell me what the equivalence relation means? Or you can type, or anyone want to try? I can give you a hint. There's 3 criteria or 3 definitions, 3 statements for equivalence relation. So I want to write it down here, equivalence. Anyone remember what's the equivalence relation mean? What's the definition it need to satisfy to be a equivalence relation? No one? Or people still typing?
Reflexivity, transitivity, and symmetry.
Okay, so reflexive. So let me just use the X and Y, right? So it means that X, if you take X, right, it need to be equivalent to itself, right, for all the element, right? And then second is symmetric, right? So if X is equivalent to Y, then you need to make sure Y is also equivalent to X. And also transitive, right? There's a, if X equivalent to Y and Y equivalent to Z, then it means X should be equivalent to Z. right? So it's reflexive, symmetric, and transitive. Okay, so don't forget, I mean, this is not only you're going to see this equivalence relation in topology or algebra, sometimes in analysis, you're also going to see it as well. So you definitely don't want to miss this. Okay, so now with this equivalence relation, we can define a spatial space. Okay, so you're going to see this notation a lot. So we use this X slash or quotient like the delta. This is a spatial space, or actually I should say a set to begin with. So this space is actually a set of all the equivalent class, right? So essentially it means that you have all the equivalent class you can pick out, and all the element in this quotient space is essentially the equivalent class. So you essentially collect all the possible equivalent class. Okay, so now we can define a typical projection map here. Okay, so I mean, I'm going to use pi a lot to stand for like different type of projection map or quotient map. Okay, so I define this map pi. It's going to map from X to this set of all the equivalent class. And as you can imagine, that the natural way to define it, the reason we call it projection map is that if you give me an element X, I'm going to map it to its equivalent class, right? Because this is the thing that live in this space, in this quotient space, right? So you can imagine that this map, first of all, this map is definitely surjective, right? Because you just pick out an element and map it to its equivalent class. Of course, you can reach all the possible equivalent class you want, right? But you can also imagine that this map is not going to be one-to-one, right? Because if you take two equivalent elements, then they're going to map to the same equivalent class, right? So if X is equivalent to Y, then they're going to map to the same class, right? Because the target, the output is an equivalent class, right? So this is definitely not a one-to-one map, okay? So now once you have this so-called projection map, mapping the element to its equivalent class, then we can, because it's surjective, right? So we can actually define a quotient topology on this space, on the target space, right? And this is in particular, we called it quotient topology determined by pi, okay, right? So that means what would be an open set on this quotient space? The open set on this, so maybe let me write down. So U in this space is open if the preimage is open in X. That's the quotient topology, right? Oops, sorry. Right? So we are going to equip this spatial space, the set of all the equivalent class with the quotient topology. Okay, then this pi becomes our quotient map, and we call this space a quotient space. Okay, so whenever you see this space, most of the time we equip it with the quotient topology, unless like spatially specified. Otherwise, whenever you see this type of space defined by a equivalence relation, then we usually use a quotient topology. That's why we call it quotient space. Okay, so if you took algebra before, then you already see this before. So now I want to give you a slightly more concrete example how to visualize such type of space, right? So let me just use this more like simple example. So let's take X, this space, to be 0, 1 interval. Okay, closed interval here. And I can define an equivalent class here. I said X is any point in this interval is equivalent. Either they're the same point or they're the end point, right? Either they have to be the same point, or either X and Y, any one of them is the end point 0 or 1. So this might be too fancy or too abstract to think about. All it says is, because it's only points between 0 and 1, right? So itself is equivalent to itself, right? That's for sure. So the only thing that we can really identify is 0 is equivalent to 1. So now can anyone tell me, can you imagine you have an interval from 0 to 1 and you identify 0 and 1 together? That's the only thing you identify. What would be the quotient space here?
S1.
S1, right? It will be a circle, right? So think about it, like you want to identify 0 and 1 together, meaning they're the same thing, right? So you can think of trying to glue them together, right? Tie them up because they're the same thing. So you can think of, okay, 0 and 1 is the same thing. So it becomes the circle. And you can think of this is either 0 or 1, right? This is the quotient space. So this circle would be the quotient space. So this is going to be the circle. Or usually we call circle to be S1, right? Okay, I want to stop here. I know I'm a bit fast here. So I want to make sure that this makes sense to other people, because if this is the first time you see quotient space, in my opinion, quotient space, you need some time to kind of think about it or visualize it. Actually, I want to tell you other type of quotient space as well. Let me pull it up a little bit so I can, hopefully this will give you some intuition. Okay, so let's see. So actually another way to do it, this is another example. So the torus that we know, right? Torus, let's just talk about this two-dimensional torus, right? The donuts we know, okay. One way people represent it using quotient space is that if you look at an interval from 0 to 1 and 0 to 1, so this is essentially, think of this type of interval in R2. And I'm going to just do a quick, like a sketch here. If you identify the upper edge with lower edge of this square in this direction, right? From left to right, you identify all this point here. And also identify this, right? The left or right edges, right? Through in this direction. Then this is going to be our torus, homeomorphic to torus. So how do you think of it? When we say identify or essentially equivalent, that means you kind of glue them together because they are the same thing. So you can first glue the upper edge to the bottom edge. That becomes a cylinder, right? And now you do the essentially glue the other circle, right? So you first glue together upper and lower edge, then you become like a cylinder, right? Now you say that, okay, I also want to glue the other two ends together. So that's essentially how you come up with a torus. So you can actually define a torus through an equivalence relation as well. And that's essentially, you can see that that's why it's also S1 cross S1. Okay, because you can see that once you identify 0 and 1, this become S1 and this has become S1, right? That's why you can view torus as a S1 cross S1. That's essentially kind of confirmed with what we know earlier. Okay, so there's so many interesting example with which comes from a quotient, or which actually is a quotient space. I mean, I'm going to introduce a couple more later on. And actually through quotient space, you can actually come up with several interesting examples. For example, if I have time, I will come back to this. I'm not sure whether I have time. You can actually create an example using equivalence relation where it's actually not a Hausdorff space, right? It's a topological space, but not Hausdorff. So with this tool, you can actually create some non-trivial example, right? So that's why it's actually very important for you to know the quotient space or quotient topology. So now I want to move to my important example for today. So before that, I need a little bit extra tool definition here. So if you have a map F from X to Y, right? Not necessarily continuous, just a map, right? I said a set U in X is saturated, means that with respect to this function, means that U can be represented as the preimage of some set V from Y, okay? So this is just a definition, but it turns out that an important remark that in fact, you can prove if it's saturated, then actually you can solve or prove actually this is true. So you will see that actually in the back of the textbook, they use this definition instead of the first one instead. So it's an equivalent definition, right? So you can say that it's saturated if it can be the preimage of some set, or actually it can be the preimage of f of u. Okay, either way it's the same, it's equivalent. Okay, so now before we really see the example, the projective space, I just want to say that with saturated set, what would be this, if you have a quotient map, what would be the preimage of a set in the equivalent, in the quotient space looks like? It's essentially you're just collecting or taking the union of all the possible element in the equivalent class. Okay, this is just a definition of how do you define such a saturated set from the quotient space. Okay, now finally, the example that I will want to talk about today. I think that's probably the last thing I could do today. So now I'm going to introduce, if you already took some topology class before you, or I don't know, maybe some algebra course before, you probably already see this, this example. So this is what we call n-dimensional real projective space. Okay, if once you see this projective terminology, you kind of know that this is in some sense related to quotient space through the projection map. And we use this notation RPN. R stands for real, right? P is projective, and n dimension, right? So sometimes that people might use the abbreviation P to the n, okay? Also stands for projective space. But sometimes we put this R to distinguish from complex projective space, CPN, okay? So CPN is, in some sense, a stronger space which has some complex structure, okay? So now I'm going to define real project RPN through quotient space, okay? So first I need to tell you what's my original space X. It lies in R to the n plus one without the origin, okay? Origin is not one of the things we want. And so you have a topological manifold, which is essentially everything but zero. And I want to define an equivalence relation. I say 2 points in R to the n plus one without zero is equivalent if y can be represented as a multiple of x. What does that mean? It means that these 2 points lies on the same lines where the line passing through the origin. So if you have some, let's say I'm taking 3-dimensional space as, for example, and if you have a line passing through zero, right? And this is y, this is x, right? They're on the same line, so they're multiple of each other. Then we say these 2 points is equivalent, okay? So they're on the same lines through origin. This is essentially how do you view it geometrically. So you identify anything on the span of this vector x, right? So in some sense, how do you view the element in the quotient space, right? So first of all, now I have this equivalence relation. So I define RPN as the quotient space of this x, this space x. And it will equip with the quotient topology we discussed before. And you can imagine the projection map pi, the quotient map pi is going to be from x to the quotient space. And it's just simply mapping x to the equivalent class. This is very, I remember the first time I studied this or see this example, it's always got to me that it's very hard or sometimes very subtle to view what the space really looks like. You can think of RPN as a collection of a bunch of lines, right? A bunch of lines, and all these lines are passing through the origin, right? Which means that anything on the same line is essentially are the same thing, right? So essentially each line is the representative, right? Each line is a equivalent, different equivalent class. So you can think of this as a lines spanned by x, right? So you give me a point, I send it to a line. But you need to be careful. It's not really the traditional line we think of, right? Because line is technically a one-dimensional thing, but we are actually thinking as if it's a one equivalent class. It's a one element in the quotient space. So you want to be a little bit careful here that it's not really the usual line we think of, okay? So now this is the RPN, okay? So I'm going to be a little bit fast here because I can tell you that even I go through like every single detail, I mean, it's very hard to right away get it, especially if you haven't seen this example before. It's very normal. You need time to absorb all these things. So the best way to do is after today's class over the weekend, study all the example I mentioned in the class, especially this one. It's going to take some time to like, absorb and then digest all the definition here. Okay. So if you're kind of fine with this projective space, then you can imagine I'm going to prove that this quotient space, or essentially the projective space, is a topological manifold. Okay, so but I'm only have time to prove the locally Euclidean, and locally Euclidean is actually, I would say that in my opinion, the most important and interesting part. So I'm going to leave the Hausdorff and second countability as exercise, and I think I might actually want to put it as part of the homework, and I will give you more hints on this one. Okay, but you can actually think about it, how to prove Hausdorff and second countability. It's not automatically true from the quotient topology. That's the unfortunate part. Okay, so I need to tell you that with product space, it's automatically, kind of automatically, right? If you have a bunch of topological manifold, which are Hausdorff or second countable, the product of them is going to be Hausdorff and second countable. And also same as subspace topology, right? But with quotient space, it's not automatically true. It's not actually always true. So that's why you need to be a little bit careful. This need to be proved. It's case by case, okay? So this is the subtlety here. So now I want to show you how to prove that this weird projective space is locally Euclidean, which means I need to find you an open set that's homeomorphic to Rn. So now you can see that this is a little bit interesting. To define RPN, you need to use R to the points in the R to the n plus one, right? So for example, what I just drew the picture here, right? You have a bunch of lines. So this is sitting in R3, for example. Then if you collect a bunch of line, if you view line as one element, that's the equivalent class, then this is what we call the RP2, right? So usually if you want to kind of somehow visualize RP2, you need to draw R3, picture in R3, right? So in some sense, it's like you need a little bit one dimension higher to visualize it. But it turns out that it's actually an n-dimensional manifold, okay? So first I need to tell you what's the open set I need to define here. And if you already read the textbook, you can see that they really, really rigorously do it in the sense that they really write down like a very detailed, like what's the definition of each open set. We want to do it right. So first, let's define this open set Ui tilde in the ambient space X, okay? To be the set of all points, like if you have coordinate x1 to xn plus 1, I want to collect all the points where xi is not 0, okay? So this is an open set. You can imagine anything but xi equals 0, okay? So this is definitely open, right? We know that this is an open set in R to the n plus 1. Now I want to define an open set on RPN, right, in the quotient space. And this open set is actually what we call the UI here. And this is the open set that we want, the coordinate chart, essentially. So this is actually just the image of Ui tilde, right? So image of Ui tilde under pi, right? So pi is the projection mapping from R to the n plus 1 to the RPN, right? So the image sitting in RPN, okay. But the question is, intuitively, if you draw the picture, you can see that it's definitely an open set, but you want to rigorously show it or prove it in some sense, right? we all know that a continuous map may not map open set to open set, right? So you need some justification, right? So first thing we observe, right? This is something I should probably say you should prove that this UI tilde we just defined in R to the n plus 1 is actually a saturated set. And I mean, we already know it's open, but it's saturated, meaning you can actually solve. This is something you should check, that UI tilde can be written as the preimage of pi of UI. UI tilde, sorry, I should do that. There's a typo here. Okay, so now if UI tilde is, so we already know this is open, right? And it's saturated. And it turns out that a quotient map will maps saturated open set to an open set. Okay, it has to be saturated to start with. Okay, why this is true? Okay, so I'm essentially trying to explain the proof here. So if you already know UI tilde on the left-hand side is open, and you know what's the topology on RPN, this is quotient topology. So now think about what's the definition of quotient topology. Quotient topology says that if you have something, right, if that's called the set V, right? If pi inverse of V is open, which is the case, then V should be open in quotient topology, right? So in this case, then pi of UI, which is essentially the V here, should be open, essentially due to the quotient topology we define, right? And what's pi of UI tilde? Keep forgetting this tilde. Then this is essentially, maybe I should call it just UI, right? So that's why UI is open, okay? So if you read the textbook, you will see that it's very dense. The proof is very dense. There's a lot of detail you need to think about. So when you read this example later on, each step, you should ask yourself why this is true, right? How can you prove it? And you might need to use a lot of some of the theorem or proposition from the back, okay? So now I'm going to be a little bit sloppy because if you really want to prove every single thing, there's no time. So I'm going to just quote one of the theorem in the appendix. So since we have a saturated open set here, which is UI tilde, then by one of the theorem in appendix, it tells you that if you take this quotient map, the original quotient map, and restrict it on the saturated open set, then it's going to be a quotient map, okay? So, I mean, generally, you don't know whether restriction of some quotient map is quotient map or not, right? But we can prove if you restrict the quotient map to a saturated open set, then it's going to be a quotient map as well. Because we need this specific map to be quotient map, then we can use the characteristic property that we mentioned before. Now I can finally define the homomorphism that we are looking for. So you might wonder why we want to go through this pi. The whole point we need to define or use this pi is that we need to come up with an open set on RPN, right? Which open set? The UI here, right? And how do you know UI defined here is really open? You actually know it's open through the projection map pi, through the quotient topology, right? If you want to really do it rigorously. That's why we need all this pi here. And now we can define this, the homomorphism, the coordinate map that we are looking for. And for each UI, I have the corresponding phi here. And it's indeed mapping from RPN to Rn. So this is the map we are looking for, that we want to prove that it's continuous. And also we want to find it an inverse for it. And then we want to show that the inverse is also continuous, okay? So this map is kind of weird, right? If you think about it. So now any point you plug in is in RPN, right? So we represent elements in RPN by this equivalent class. Okay, so this is essentially equivalent class here. You plug in an equivalent class, which actually has coordinate 1, 2, all the way to x to the n plus 1. Okay. And what would be the output? Output should be a point in Rn, right? So you can only have n coordinate. So you can see that now you have x1 divided by xi, x2 divided by xi, and up to I minus 1, you have I minus 1 divided by xi, and you skip the I, right? And you jump to I plus 1 divided by I, right? So you can count they're actually n coordinate, okay? So now the first thing is that a lot of people overlook is that why this map is well defined. Whenever you define a map on a quotient space defined through an equivalent class, you need to first make sure it's well defined. What does that mean? You need to make sure if two elements are equivalent, right? So let's say if you have 2 points are equivalent, right? Then they actually represent the same equivalent class, same element in your RPN, right? So you want to make sure if y is equivalent to x, if you're plugging into this phi, right, then phi of y should be equal to phi of x, right? You want to make sure this is the case. Otherwise, the map is not even well defined, right? If you're plugging two elements in the same element, same equivalent class, it's better get to map to the same thing, right? So how do you check this? You can show it. And so essentially what we want to show is that you want to make sure when you plug in the equivalent class x into phi, it will be the same thing as you plug in anything that's equivalent, meaning any non-zero multiple of x, right? Because what does that mean for two things to be equivalent in this case? That means they're multiple of each other, right? They're on the same line, which the line passing through 0, right? And actually you can just eyeball from the map, this is automatically true. Because if you plug in x, right, if you have some coordinate, and there's another coordinate, you have lambda times x, right? And you can see that because we are dividing xi, right? So what's the new thing? If you plug in lambda x, it's going to be lambda x1 divided by lambda xi, lambda x2 divided by lambda xi. So the lambda will actually cancel out, right? So automatically you can just quickly check that this map is well defined, right? But you should always check that, right? Otherwise there might be a problem. Okay, so this is actually the first thing. You should do it yourself. Like this is actually important. Okay, so whenever you work with a map from the quotient space, you should always check the well-definedness. Otherwise, there might be a problem. So now I want to show that phi is continuous, right? So essentially, that's my goal, one of the goals. So I want to show phi is continuous. But you can see that since I input the element from RPN, it's very hard to directly, rigorously set what an element in RPN looks like, right? It's an equivalent class, right? It's not just a usual point in Rn. So how do you say it's continuous? Then we really go through the quotient map, the projection map pi, right? So this is where you can see the diagram again, right? This is the characteristic property. So you can see that now we have this quotient map, which is essentially restricted on UI delta. So this is actually from the ambient space. So let me give you all the space, right? And this UI is sitting in RPN. And this phi is the phi we want, right? And you have the diagram here. So you can see that now I want to show whether this phi is continuous or not. But I already know I have a quotient map here. So remember the characteristic property, characteristic theorem we just proved. Then the only thing I need to check is whether the composition map is continuous or not, right? If I can check this phi of pi is continuous, then we are done, right? Then we can, by using the characteristic property of quotient map, then we can essentially show that phi is continuous, right? So because we already know this pi is a quotient map. So now we really directly, explicitly see what this phi of pi looks like, right? You just really plugging in. So what's pi? Pi is mapping. So I'm going to break this into two steps, right? You start with So pi is you start with points in Rn plus 1 quotient 0, right? And you through pi is a projection map to Rpn. And that's essentially mapping to equivalent class, right? And then this is pi, and you go to phi, right? So I try to break it if you forget the definition, right? And you can see that this map is explicit, right? It's from a point in R to the n plus 1 to another point in R to the n. And keep in mind that all this xi, because the domain is ui tilde, so xi is not 0. So of course, you can just explicitly see the map, right? It's a map from some Euclidean space to Euclidean space. So we can directly see this is definitely a continuous map, right? So, I mean, this is continuous. This map is continuous. So if this is continuous, then by the characteristic property of quotient map, this is continuous. So we know phi, each phi is continuous. Okay. So now I'm going to stop here because I'm run out of time. So the only thing I left with this example is I can actually define what inverse map is, a well-defined inverse map. And I can quickly set that what the inverse map looks like, and I can check it's actually continuous. Okay, so I'm a little bit slow today because I think I'm providing a lot detail here. So please do me a favor, start reading this example here and read further. So next Tuesday coming back, I'm going to do pretty much focus on topological property like compact, pair compact, connectedness, proving a little bit things. I don't have time to prove everything. So you want to start reading some of the theorem there, and once you read it, and let me know whether there's a problem, question, because I may not have time to go through every single proof in the theorem, especially the one that's already included in the textbook. And I'm going to also focus on the smooth structure, right? Once we know topological manifold, we can introduce what a smooth structure is. And I will provide more example. Once with the smooth structure, then you can define what a smooth manifold is. So pretty much over the weekend, start working on some of the example, review your topology, and read ahead. Okay. So let me know if you have any question. Otherwise, you're free to go. Questions? Thank you.